In the previous video, we demonstrated the first fundamental theorem of calculus. We saw that differentiation undoes integration. In this video, we demonstrate that the reverse statement is also true. The second fundamental theorem of calculus is the name for the statement that integration undoes differentiation. We want to show that the integral from x sub d equals a to b of df dx at x sub d equals f on b minus f on a. The integral of the derivative of a function equals a difference between the function evaluated at the final endpoint of the integral and the function evaluated at the integral's initial boundary. As with the previous theorem, we pursue a graphical argument. We draw both a plot of f on x versus x and a plot of its derivative df dx, here using the variable x sub d to label the values of x at which we evaluate the derivative. The integral we have written is the area under the plot of df dx versus x between x equals a and x equals b, which we can approximate using a collection of rectangles. Look at the rectangle at x naught. Its height is df dx at x naught, its width is delta x, and so its area delta a is df dx at x naught times delta x. Hugging the plot of f on x versus x with a staircase, we identify a right triangle with the left-hand corner at x naught drawn with the same width as the rectangle below. If delta x is sufficiently small, the ratio between delta f and finite delta x is close to the limiting value df dx at x naught. Thus, the height of the triangle delta f approximately equals df dx times delta x. But df dx times delta x is simply the expression we obtained a moment ago when calculating the area delta a of the rectangle with left edge at x naught in the plot at the bottom. Thus, the indicated height delta f in the upper plot roughly equals the area delta a of the rectangle indicated in the lower plot. Likewise for the rest. Because the heights of the triangles correspond to the areas of the rectangles, adding the heights of the triangles is a proxy for adding the areas of the rectangles. Add the heights of the right triangles vertically. Their sum equals the difference between the height f on b and the height f on a. Adding up the lengths of the golden arrows is equivalent to adding up the areas of the turquoise rectangles. We have demonstrated that integration undoes differentiation. This is the second fundamental theorem of calculus, which we sought to show. As we will see on the next slide, the theorem that we have just demonstrated allows us to generate a table of integrals from knowledge of rules for differentiation. When we studied derivatives, we made a list of patterns to memorize so as to avoid repeatedly deriving the same results. We follow the same strategy when working with integrals. This is an example of the kind of listing and formatting typically encountered in published integration tables. How did we generate these particular formulas? We inferred them using differentiation rules we had previously encountered and using the second fundamental theorem of calculus. The pattern we just demonstrated is that the stuff inside the integral on the left is the derivative of the stuff on the right. We format differentiation rules we already know into this pattern. A rule for differentiation is a relationship between a quantity that is to be differentiated and its result. We place the results on the left and the quantities to be differentiated on the right. To become familiar with abbreviated aspects of this notation, we more carefully obtain the entry corresponding to the power law, meaning the entry corresponding to functions with association rules of the form f on x equals x to the n. From our previous work with differentiation, recall the rule for taking derivatives of power law functions, namely df dx at x sub d equals n times x sub d to the n minus 1 power. The mnemonic instructs us to bring the power down in front and to subtract 1 from it upstairs. According to the second fundamental theorem of calculus, the integral of a derivative spits back out the original function's association rule, more specifically the difference between the original function evaluated at the final and initial boundaries of the integral. In this example, the original association rule was f on x equals x to the n. Evaluating f on x at b gives b to the n, and evaluating f on x at a gives a to the n. Taken together, this gives the difference b to the n minus a to the n. This is a longhand way to write out this integration pattern. Entries in the integration table are written in an abbreviated format that saves ink. Relabel the final integration boundary, or so-called integration limit, x instead of b. Suppress the subscript and superscript adorning the smooth s, suppress the subscript d, and replace the minus a to the n with instead plus c. This c stands for a quantity that is constant when the value of the initial boundary a is constant. We have now explicitly obtained the first entry in the integral table using our previous knowledge of a differentiation rule for power law functions. When using an integration table to write out a definite integral, be aware that some notation is implied and needs to be unpacked. The smooth s's are missing the subscripts and superscripts that would denote the initial and final boundaries of the areas of integration. Because these abbreviated patterns are missing symbols that can remind us to be clear about the locations x equals a and x equals b of the boundaries of integration, we can call the abbreviated patterns found in tables indefinite integrals as opposed to definite integrals. Before we continue to the final video, we need to present an alternative way to talk about the abbreviated notation found in integration tables. We introduced the concept of an antiderivative. Rather than maligning the indefinite integral as though it were merely the result of forgetting to write down symbols in a definite integral, one often says, instead, that the pattern smooth s little g on x dx equals big G on x plus c indicates merely that taking the derivative with respect to x of big G plus some constant with respect to x c gives little g. Slapping the smooth s and dx on little g on x is a way to notate the question, what could we have been working with before a derivative was taken that yielded little g on x? What happens if we undo the action of the derivative to figure out from what expressions we could have started? The string of symbols composed of the smooth s, the little g on x, and the dx all written together, in the absence of any subscript or superscript attached to the smooth s, is often called the antiderivative of little g on x. This pattern of speech does not require explicit discussion of the notion of the area under a curve with well-defined initial and final boundaries. In this video, we demonstrated that integration undoes differentiation. This is the second fundamental theorem of calculus. We used this theorem to begin building an integration table from known rules for differentiation. We can use this table both when we are trying to calculate definite integrals and when we are trying to figure out the antiderivative of a function. For both applications, the procedure is to look through the integral table for the indefinite integral we want to study. Sometimes the indefinite integral we seek might not be found in a table because the solution is not known. At other times, however, it only seems that we cannot find a useful listing in the integral table, and only a minor manipulation is needed to re-express the problem at hand in a format that is obviously listed. We expand on this point in the next video.